So everybody hold questions. We're gonna start the talk. And so I'm very happy to have Zheng Yuan Dong give the talk today. She's my first PhD student here. And she's gonna talk on some exciting new work we have on model lakes. And
yeah, thank you. Thanks everybody for coming. And today I'm going to talk about our project, the Semantic Table Discovery in the Model Lake. And I'm Zheng Yuan, the second year PhD student and supervised by Professor Renee Miller. And this is also my first PhD seminar talk. So before going to introduce about the table discovery, we are going to first introduce what is data lake. So I believe most of you have heard about the data lake concept before. So you might have a puzzle, what is the difference between the data lake and the data set? So we begin with an example. So imagine that you are a data analysis hired by one bank, and your team asks you to develop some fraud detection model based on their databases. And you come to the databases and found hundreds of thousands of tables in it. Some table might record the card application data before application, and some might record the card usage data, and some might record the bill payment data. And each table might consist of tens of hundreds of attributes. So before your developing this model, you need to first do some feature engineering work, like feature selection based on it. But on the table level, that is to select those tables that are most related to your targeted. So this is called table discovery and data discovery. And then when you get some tables and you see some column named ID, but you don't know whether this ID refers to a driver license ID, or it is an identity number, or it is some unique numbers that used within this bank. So you need to refer to some developer document to refer what each column's meaning. So this is called metadata management. And then since bank will renew their data periodically, for example, each time when user have new data of card usage, and the bank will update card usage data daily. And in each bill payment date ended, and the bank will update bill payment data monthly, and they might get some third-party credit score, which consists of other banks' card usage data, and they will update this table monthly. So each time when bank trying to update some data, they will keep a snapshot of current status of data because they want to keep the safety and repeatable to guarantee it's repeatable. So this is called the data versioning. This trying to solve a problem that so for one table, there are many copies of this model, of this table stored in the database. But however, a large part of overlapped part, it is repeated. So whether there is a case, we try to optimize our storage by only storing this overlapped part and with the difference between the versions. But there introduced another problem is that when we try to use a specific version, we need to recover from the compressed status. So the data versioning tries to find a balanced point between the optimization in storage and the recovering algorithms. And after the data analysis get one table, they might found that some attributes come from the raw data, but while other attributes they are not. So they need to go back to the development document to see where these new attributes coming from. And they can see that some attributes is derived or computed based on other attributes. So this kind of semantic annotation between different columns is recorded in development document, and this is called the semantic annotation. And when this data analysis tried to do some coding work, and suddenly he found a bug. And for example, she was checking the age column and found an 1000 number in it. So we think, we all believe this is ridiculous for human age to have a 1000 age. So she go back to the table and check and found there is a shift between different columns. So this means that before developing this model, the developer needs to first do some data cleaning before that. So these are all tasks that introduced over the data lake. So comparing to it, the data set, is a well curated and well cleaned and maybe consists of the structural information of each items, which means that the structure of each items might be same, which is different from the data stored in data lake. And then we are going to introduce how we do the table discovery. So here we put the information retrieval as an example. So for the information retrieval, the input is a text in natural language or question in natural language. And the aim is to retrieve the corpus, the text from the local corpus based on the similarity of semantic information. So since similarly, when things come to our table discovery, the input is a table, and the aim is to find the table candidates from local data lake, which follows some schema-based information or rules. And here are some tasks that following this pipeline in the table discovery task. The uniable task aims to find the table candidates that can be uniable or concatenated with the query table. And the joinable task aims to find the table candidates that can be joinable or integrated with the query table. And for the annotation, we might refer to the other tables with already annotated relationship to get this kind of relationship to annotate our query tables pair of columns. And there are also other tasks that don't strictly follow these rules. For example, the keyword. For keyword search, the input is a short token instead of a table. And it also aims to retrieve the table candidates from the local corpus. And for the versioning, we just introduced, it tries to find a balanced point between the optimization, storage, and the recovering algorithm. And for the disambiguation, so here we take an example. Imagine that if two people, they are working on the same table, but they both annotate a same column in the same meaning, but in different names. In this case, if we want to use these two tables, we need to first do an alignment on these two columns because they have the same meaning, but in different names. So this kind of task is named the disambiguation. And then we get an initial understanding of the table discovery, and then we are going to introduce the model lake. So here is a figure, summarized figure that comes from the survey paper of our lab's previous work. So here introduced the current tasks that define over the model lake. First is document generation. It tries to regenerate or extract some information related to the performance of models or the configurations information of the model and other descriptions or semi-structured description of the models in it. And the auditing aims to present the risks of the model. For example, whether this model, what is generation ability of this model on new benchmark, will it have some privacy leakage issue, and whether if it is a language model where it says something that illegal or rude. And for the citation task, this aims to develop a citation graph based on the model level. For example, if one model is transfer learning based on another model to freeze its weights and add several layers on top to do the fine tuning, then these two models are kind of related and can be regarded as an successor and disaster. So this task also includes the model versioning tasks. But what's different from the data versioning part is that model versioning can actually utilize the data versioning because model is trained and inference on dataset. So it can use the both level of citation graphs to try to do something. And the model search aims to retrieve or search for the models that's suitable for the user's goal described in language or other things. And here we introduce two detailed tasks based on the model lake search. So one is the content-based model search. Imagine that you have an image, you have yourself selfie, and want to turn it into Ghibli style. So you pick GPT and Claude and Gemini and DeepSeek and want to check which model can synthesize the Ghibli style image that you want. So you use 4 models to run 4 different image output, and you then compare the style on the output and determine which model is you wanted. So this tries to compute some semantic semantically score based on the output image. And another task is the metadata-based model search. So it's based on the document recording the metadata of a model, like performance or description or configuration, how many parameters this model have, or what's its scope, and then do the information retrieval based on it. And after knowing the data lake and the model lake part, we can observe that there exists some gap between them. So over the data lake, the input and output is tables, but however, over the model lake, currently the input output can be text, can be image, but they cannot be tables. So it inspires us whether there is a way trying to bridge them by finding tables in the model lake, and so that we can embed all the techniques from the data lake towards the model lake. So in order to solve this question, we prepare 3 research questions to address it. The first question is that whether we can find the representative tables over the model lake to describe the model fully. And the second question would be how to find the relatedness among these tables, because after we embed these techniques into the model lake, and then we need to do some evaluation on it. And the third question would be, even though we indeed retrieve some model, what does it mean in this domain? So next, we are going to address these 3 questions in our work. So the first question, we first start from the Hugging Face, because Hugging Face is one of the largest public model lake that hosts models that developed and published by the researchers. And it is just like the GitHub repositories. It will have a repository holding its model file and also present a model card like a README file in the GitHub. So we take the BERT repository as an example, and fortunately, we indeed find some tables that can present the model performances and configurations, like the number of hyperparameters and which kind of language it worked on. So here we come to the assumption, each model has performance or configurations tables. So this also aligns our intuition that the researchers, after he or she fine-tune a model, and he also want to use some structural information to present or sell its model to other users. And then we try to answer the second question, how to find the table relatedness. And also by observing this BERT's model card, we also find that sometimes some model card will obtain some BibTeX references, which links to the report, peer-reviewed report of this model. So this also aligns our intuition that because training a model or fine-tune a model, it requires a lot of time and resources. So it is of a high possibility that it was developed by an organization or individual researcher. So their aim is to have wider impact and let more people use it or know it or compare it. So it's of high possibility they will generate some report, maybe a Jupyter notebook, maybe a peer-reviewed paper on it. So here, to simplify, we keep the assumption that the model is likely to be accompanied by one paper. And there is other cases that if one model is fine-tuned on another model, and the model A has paper accompanied, but model B don't have, then how to solve this problem? We also observe in the model card that sometimes some model cards have links towards other model cards, because it is a variant version of another model card, maybe a quantized version, maybe a fine-tuned version. So this also provide us information to find this kind of model relatedness between models. So here, we can infer the table relatedness from both the paper relatedness and model relatedness. So for the paper relatedness, after we get each paper that related to this model, we can utilize the paper citation graph as a relationship to link to try to annotate the table relatedness that exists in this model card. And then we try to solve the third question. So after search, what does it mean on our query table and retrieve tables? So here is an example that we manually selected from some references. So they all come from the pre-trained language models. So the BERT, the Roberta and Electra, they are all very famous language models, and each table, their table stands for the same meaning. Each row stands for the performance of one baseline models, and each column stands for one subtask on the glue. So glue is a benchmark developed in the natural language area, and it consists of I remember it's 9 subtasks. So here by this, so they are definitely uniable because their columns are most overlapped and aligned. So here, the findings we get is that by uniable these 3 tables, we can compare different baselines on the same benchmarks. So here we comes up this assumption on this. And here is another example on the joinable case. So here, the adversarial glue is a new benchmark developed over glue. So it is a new benchmark paper. And we can observe that there exist some columns beyond the glue. So here, and we can observe the most of its rows is overlapped. So the joinable search, according to our assumption, it can interpret the old baselines or old models on new benchmarks. So these are 2 examples that we find try to interpret the meaning of searched tables over the model lake. The performance, accuracy performance of this model on this task here. And some might record the training flows is some configuration of the model. And
so for things like union-ability, you need exact attribute match, right? Only then you can union in the first case. So if you have how do you does it if somebody has not have they don't have 2 different measures, for example, then you, in terms of at least relational semantics, you cannot really union those 2 tables. Would that be a problem? Or
Yeah.
how do you
Well, yeah, the relational definition of unionability is it has to have the attributes of the same.
yeah.
But in unionable search, because these are heterogeneous tables, we relax that. They don't have to have the same name, they have to have the same semantics. So there's different signals that you can use to determine if they have the same semantics.
I see.
Yeah.
Is it like do you have a quick can you give a quick intuition on how do you identify?
Since this isn't Dora's work, maybe I'll
Okay,
say it.
you can.
Yeah, you can, one is overlap of values, so which, like the string values, if they overlap, that might indicate they might have the same semantics.
Okay,
Another is if you can map up into an ontology,
okay,
if they have words
I
from the
see.
same class of an
I
ontology.
see.
And then another is that you take their word embeddings
And put it in the
and
first
if
stage.
they're very similar word embeddings. Numbers are a bit harder, so,
Yeah.
but maybe we'll take that
Yeah.
offline.
Yeah,
But that's,
Okay.
how it's done in data lakes because they're so heterogeneous, yeah. And also, they don't have to have the same number, so people do essentially outer union rather than union.
okay,
So if one table has a few more attributes, it's okay.
I see.
Yeah.
And next, we are going to introduce the methodology in our work. So in order to solve the first question, how to find the tables, and we start from the model card, from the Hugging Face set. So we can see there are several elements that provided by this model card. The first is some tables, and it also provides some URLs that might link to other resources like archive, GitHub, and other PDFs. And also it has some links towards other model cards or dataset cards. And it also provides some references sometimes. So, but the table here is not fulfilled because sometimes in README files, the developers or researchers, they only want to present the most condensed information to attract the user's attention in the first glance. So they may not put those ablation studies tables or the full the whole completed tables in their model class. So in this case, we want to get some other tables as complemented from other resources. So we go from those URLs to go to the archive platforms and GitHub platforms. But however, there is an issue. When we try to extract the tables from PDFs, it is very time consuming and resources consuming. So here we choose the HTML version, which is easier to crawl. So for the GitHub, we pick their README files and extract those tables. And sometimes there exist some references. They don't have an archive version because they follow some double-blind requirement and they directly published in those conferences. So in this case, we extract those titles and go to the Semantic Scholar platform to do some references and get their full test. But sadly, there is a case that their provided full test loses structural information, which means that they only include these numerical values or string values and loses the structural information. So here we use a large language model and tries to recover its structural information from it. And then this is the first step for finding tables. And in order to prepare for the next question, how to find the table relatedness. So here we need to first get some tables or titles from the model cards. So the first reliable resources would come from the references. And then we get the titles of the model cards. And then also the titles from the archive and also the titles from the GitHub. And also the bytecode references from the GitHub README file. And we get all these of titles, but sometimes these titles are not valid paper title. So we get this table set and go to the Semantic Scholar platform to do some reference to get their references list and citation list. So this is what this crawling pipeline do. Oh, sorry. And then we present some statistics that trying to compare our benchmark towards those classical benchmarks developed over the data lake. So and here are the 5 benchmarks coming from the data lake in the first cluster, and the different colors in blue stands for our tables in our benchmark coming from the different resources. And the 4 clusters stands for different status of our benchmark. So first we get all tables, and then we found there exists some duplication cases over it. This might be because that same author might present the tables in their paper, and in order to broadcast it, and they put some tables in their GitHub page and in their Hugging Face page. So in this case, we need to do a deduplication. And another case is that if I just want to fine-tune the model based on another repository, then I fork that repository without changing anything. So this case will also introduce some duplication. So next we take a deduplication step, and then in order to build up the ground truth to do some evaluation, we need some titles. So then we do a filtering with those tables with the titles. And finally, as we want to build valid ground truths from Semantic Scholars, references, and citations, we need the valid title, the tables with valid title. So here, the findings come from this statistic table would be, first of all, our final benchmark will consist much more numbers of tables comparing to most of the benchmarks introduced in data lake. And the second finding would be that our numbers of rows would be much less than comparing to those benchmarks in data lakes. This is understandable because the peer-reviewed report needs the most condensed information. And sometimes it has some page limited that cannot present so much information. And the third finding would be that after applying the stricter conditions, our numbers of rows goes up a little bit. This means that this can be a hint to infer that after applying these conditions, our quality of table increased a little bit.
Sorry, can I ask a question on that part? So the all part, like the average number of rows, all is, you have duplicates. You have not deduplicated, and what was the average number of rows in that case? Is that right? Before you deduplicated your tables. So when you deduplicate, you're removing, how is the number of rows going up?
There's more small tables that are duplicated. Yeah,
The average number per table.
per table, yeah. And then when the other ones, there's more small, like 1 row tables that describe invalid things, yeah.
Okay, I have one question. When you say that duplicate tables, is it like 100% match or very close?
100% match.
100% match.
Yeah.
Not like 95% off.
Yeah, no. And then we are trying to solve the second question, how to find the table relatedness. We come from the 3 different levels. So as we already introduced the paper relatedness and model relatedness, but there are some sub cases from them. So the first case that if that 2 papers, they are directly cited each other. For example, the Roberta directly cited BERT because it is developed on BERT. But there exist cases that they are not directly cited. For example, if 2 papers they are developed at the same time, they don't have a time to cite each other. And if they come from the same ancestor of work, but then deviated into different benches, then it is a possibility that they are not directly cited. But we can inference this from their references leaves overlap. And then from the model level, it means that on the model card, it have links to other model card. There is one case that if 2 models, they are directly cited each other. And here are 2 information provided on the model card. The first part comes from its model card text, and second part comes from its README, the main text part. So in its text, the official staff will try to infer a relationship between the models, whether one model is another adapter's version, the fine-tuned version, the merged version, and quantized version. So we can utilize this information. And another case is the link, the URL exists in the card README that can identify the link between 2 model cards. And there is also a case that if 2 models have the BERT as the same base model, but they are not directly related. So we can also derive this kind of relationship by our analysis. And Hugging Face also provide a platform for hosting the valid dataset IDs. So here, there is only one case that if 2 models, they are inferred, they could be trained or inferenced on the same dataset, then we regard them as related because they might come from the same domain, or at least they have the same structure of input and output. And then after we get all this kind of metadata, how do we derive the table relatedness from it? So we first go from tuple. So for each model card, we now extract several tables based on it, and we now extract several valid titles from it. And then we try to derive it from it. So take the paper relatedness as an example. We first query the semantic scholar to get the pairwise relationship between those papers, and then go back to the model card level. We then infer the model card level relatedness from it. And finally, we get the table relatedness from it. So there is a tip that for the paper relatedness, it can and model card level relatedness, they can have self loop, because given that tuple as an example, if 2 tuple have one same paper, then these 2 model cards can be regarded as related. And if 2 tables coming from the same model card, then they can be also regarded as related. But for the table level, they cannot, because this will cause the precision 1 score into 100%. So this is nonsense. We avoid this kind of self loop in the table relatedness. So here, we use the summarized figure to present this step. We still take paper relatedness as an example. So we first got the relationship of the paper citation graph, and then we get the citation graph over the model card level, and then we infer the table relatedness step. And for the other levels of citation graph, like model relatedness and dataset relatedness, we start directly from the second step and then go to the third step. And then now we present some statistics trying to compare the links count distribution in our benchmarks and the classical benchmarks over data lake. This is because that our setting is slightly different from the data lake setting. In data lake setting, the query set and the remaining pool, they are isolated. But in our case, every table is a query table, could be a query table with the remaining tables as the table that could be retrieved. So this might include a concern. How about each table can link to every other table in this table lake, in this model lake? This will cause a problem that no matter which discovery method we use, the accuracy will always go to 100%. So we need to draw a link count distribution to avoid that case happen. So fortunately, in our case, even though our benchmark has a more varied distribution of the link count distribution, but not everything goes to the worst case didn't appear that every table linked to every other table. So here we present the three level of ground truth, and all links just try to merge and combine the first three ground truth lists. And for example, here the central sludge means that every table can link to 20 other tables in their data lake. And then we also have some observations when we do the studies. So given these two tables as an example, they are not uniable at first glance. But however, if we do some transfers or transpose or permutation on the Roberta table, then we found they are actually uniable because they share the same columns or rows, like learning rate, the batch size, weight decay, something like that. So this is due to that sometimes the author find the page is too long, so they want to condense it a little bit by shifting the style of the tables. So in this case, we want to do some augmentation to help our algorithm to find this case as uniable or searchable. And there is another finding that sometimes the author might add the headers to its cells, while in the remaining cases, the tables are of highly possibility to be numerical tables. So this case will also prevent the accurate encoding and thus prevent the accurate search. So we propose two augmentation tricks here. Is that beyond the original table set, we propose two other sets. One is to add the permutation augmentation tricks on, and another is to add the header to cell augmentation tricks on. And we will only examine these performances on the ablation studies. So in the main result, we still keep the original table set. And during the studying of paper relatedness, we also observed that the Semantic Scholar platform also provide two other keys and try to describe the different citation type between two papers. So one is whether one paper cite another paper in its background or methods or results. We all know that sometimes one paper's reference list can goes up to 50 or 100. So whether all papers that are tightly linked to this paper, that is not. Some are core baselines and results that compare to, but some just mentioned in background. So this provide a more finer way to detect the citation graph. And there is another key that to determine whether one paper is of higher influence to another paper. this is a combined factor that considering no matter the how many times paper A reference paper B and whether it is a core baseline of this paper. So it is so this also provide extra information for the paper's relatedness. We will also include this part in the ablation study. And even though we just see the link count distribution, we still want to check the density over the ground truth, because if the ground truth goes to 80% dense, then it is very easy for the retrieval method to find a candidate table that actually link to the query table. So we want to avoid this case by checking the actual density. So here we can see that in the two base cases, the first finding is that by sorting the condition from direct citation to overlap, it can really enhance it can really include more relationship between the papers, thus the relationship between the tables. And by crossing more keys towards it, it can make the cases stricter and will decrease the density. So here we just present an ablation study later to present all the performances, but don't compare them, because it depends on the users. Maybe some users think the direct citation is meaningful, and some users think the overlap type with cross some truly influential citation type is meaningful. And next, we are going to introduce our experimental settings and results. So here, we use the six discovery methods coming from the table discovery method and the retrieval method, and three we just introduced the keyword search, the joinable search, and uniable search. And as default, they all work on the table. The input and output are all tables. And to compare it, we leave the dense retrieval work on the table. And there is a case that we want some metadata-based experiments to be comparable, to compare them with the table-based experiments. So here we do it like this. For each deduplicated table, and we get their copies, original copies, and their related metadata, and then we concatenate all this metadata as the representative of this table, and then we do a sparse retrieval and hybrid retrieval on these two on the metadata level, and then to infer the table relatedness. And for the implementation tool, we use the blend as the default system for keyword search and joinable search, because blend is a unified system that to integrate multiple data lake techniques in it, and it's very easy to use. But for the universal search, we use Starmie because it is the state-of-the-art techniques that developed over the universal search, which embed some semantic information. And for the retrieval methods, we use the face developed by Facebook and also Python developed by other groups in DSG. And also hyper retrieval use because our implementation is a little different from the Python, we use a cascade combination. First, retrieve top 100 candidates, use sparse retrieval, and then retrieve the top one, use the dense retrieval. And there is how about whether we include the headers of the table? So as default setting in the table discovery method, they are not included. But however, for the keyword search, we must include it because we are most time we are numerical tables. So it might not contain so much semantic information. So by including the headers, we will make the keyword search really work and comparable. And here is remember that the keyword search, the input is a short token instead of a table. And now we want to turn it to align with our pipeline that the input is table and output is table. So here we pick the tables and get it headers and then split it by each cells and use this keyword to retrieve the tables and then finally rank them by the keyword count. So in this way, we can still get them same pipeline. And also, to make it comparable, we let the dense retrieval also include the headers, because without it, it will be a combination of numerical values in most time. It can also not search some good results. And then here is our main result to present the performance of 6 methods on different levels of ground truths. And here the takeaway is that the first finding is that the uniable search we use StarMe is the best paper compared over the data discovery. And it is second finding is that it is comparable towards those information retrieval. It is understandable because table discovery methods are schema-based rules. It is stricter than the semantic-based methods. So here we draw a conclusion that all methods, they are better than the keyword search, while the uniable search still have some room for the improvement. And we can treat retrieval methods and table discovery methods as two perspectives of retrieving, and we believe they can benefit each other because one is schema-based and one is semantic-based. And remember that our tables come from 4 resources. So some might come from model card and GitHub, they are markdown tables, and the archive, they are HTML tables, and the store, the semantic scholar, they are plain text plus the large language model polished and structural information recovered. So the quality of tables are different. And we regard these 2 resources of these two resources are of highest quality of table because they maintain the original information, but for the archive HTML, it is compiled based on the LaTeX. So sometimes it might lose a little bit of information. And for the store, it totally loses information. So here we separate them and then use examine some the performance on some combinations. And here our conclusion is that the performance is really different across different resource of tables. This is because of their quality. And notify here that for the GitHub tables, since it only has 1,000 tables and its URLs appears a lot of time, much more than other resources in those model courses. So this might make its performance a little bit higher than others. So this performance is less reliable than others because they don't have so many tables and their links duplicated a lot. And then we going to examine the performance on the augmentation set. So here it is like this. We have 3 sets. One is original and 2 other are augmented sets. And for the first experiment, we combine the original set and the header to cell set and do the retrieval based on all the tables. And we evaluate it like this. So imagine that if one table and its augmented version, we get both their top 1 candidates, and only one of them steps on the ground truth, hits the ground truth, then we regard it as true. So this performance will definitely be higher than the baselines, but than the main results. But here we just want to check how much it improved based on the main results. So this can help us to address our concern that how many tables that have this kind of formatting issue. So we put the main results here for comparison. And there is another tip here that here we only present 3 methods because the 2 metadata-based methods, the table augmentation will not work on them, cannot improve them. So we ignore them. And for the summary results, since its computation efficiency is highly rely on those numbers of columns. So, and here, no matter we not only improve the numbers of tables, we also do a transpose. So remember that our numbers of rows is much more than its columns. So after the permutation, the transpose, the numbers of columns will goes very high. So this might hurt the computation efficiency. Will also skip this method at this current stage. The findings coming from this experiment is that both augmentations can work, can improve the performance a lot based on the main results. And if we apply the both augmentation in the same time, then we can see it can improve the 15% based on the main results. So the augmentations can really work. And then we're going to examine the performance, the ablation study on the citation type. So here, we also compare to its density figure. Is that we can draw a conclusion that the accuracy might be kindly related to the density. But however, when density goes very down to 3 points, but it is still not so low. So this is the case that. So here we just provide this performance for the users to choose. We don't compare them. And this also can work as a hint that our searching is robust no matter on which kind of citation types. And after done all the experiments, now we answer the third question, whether the searched results satisfy our expectation. So here is an example coming from the real cases. So the query table is sparse, and we pick the top 2 candidates from the Universal search and the dense retrieval, and we found that the Universal search can find more structural alignment. For example, there will be a combined cells named as glue, and there will be columns that coming from the subtasks of glue. But from the dense retrieval, it will include something like maybe each column stands for one matrix, not one benchmark. And sometimes it will contain some semi-structured combined columns, combined rows. So we can draw a conclusion here is that the uniable search, they both, first of all, they can both retrieve meaningful uniable. Oh, no, not uniable. The related candidate tables that can be comparable to the query table. And as our expectation, whether we can compare the different methods on the same benchmarks or compare the same models on different benchmarks or different models on the same benchmarks, it can do that. And secondly, the uniable search will find more schema aligned candidate tables, while the dense retrieval will find more semantically aligned tables. So these two methods can complement each other to find meaningful information at this time. And finally, here is some limitation of our current work as we just introduced. We haven't extract tables from PDFs yet, and our recovery of structured information based on the store is not work well, because remember it's only 30% of the performances. It shouldn't be work like that. So whether there is a better way to recover it. And secondly, currently we only work on the Hugging Face model lake, but some authors, they don't host their model on the model lake, on the Hugging Face. They will provide a Google Drive link or the Baidu Drive link to store their data. So whether we can choose other model lake or private model lake and other resources to try to expand the scope of this. And then currently we we combine the configuration table and performance table all together to do the retrieving. But is there a way that we can separate them and on different track to do the retrieving accordingly? And there is also a case that, remember, Hugging Face provides a fine-grained version of the model relatedness as fine-tuned version, adapter version, and other version. So whether we can also go to different tracks and try to evaluate it. And here is the downstream application. This is a screenshot coming from the paper with code. So this is the web that holds different tasks. And for each task, it will hold different benchmarks. And for each benchmark, it will try to hold the performance of baselines and compare them on. But sadly, it is based on the manually or crowdsourced. It relies on different researchers to contribute to it manually. But if using our cases plus the data integration, we might can generate this kind of benchmarks automatically. So here the main takeaway of our work is that we develop a novel methodology for defining the model relatedness, also table relatedness over the model lake. And here, this is the first model lake discovery benchmark based on the Hugging Face, the real machine learning artifacts. And we are the first to use the table search as a novel solution for the model discovery. And yeah, that's all. Thank you.
Regarding the relatedness. When you say that you have columns and the titles, do you have it fine tuning? Like if you have mechanism for like looking at the table, then paper, then other metadata, right? But out of say from this three skills, do you have any like parameter tuning, like which one will give you better relatedness at the end?
In our case, only the StarMate is use some fine tuning techniques in it, but it tries to separate. But it's just the fine tuning is just based on the contrastive learning, so it might not. So currently, our techniques don't include any fine tuning on specific tables.
Thank you for the talk. I can understand one thing. When you say model lakes, you're talking about large scale repositories for models, right? In this research, you are not serving the models themselves, but rather you are using the metadata tables of the models. Or did I miss it? Okay. And how large were the data sets you use or the rows you use? Maybe I missed that.
So the Hugging Face hosts 1 million model cards, and some are not valid and some are empty, and some might not include the table information or reference information as we need. And after extracting that, we got 7,000 papers, valid references from it, and 930K tables from it.
Or over 200,000 models, right?
Yeah,
So
after
Face has a lot of focus models.
And my follow-up question was like, did you have any troubles about the setting up the infrastructure? Was it too costly to perform the search? The data, if the operation was too costly or resource consumed.
Sorry, pardon the last sentence.
Question is like, did you have any problems with the infrastructure setup if the search was too performance consuming or something? Since you had to do search over multiple.
Yeah,
tables, that's essentially my question.
Yeah,
did you do like a in-service solution?
Yeah, thank you. So, yeah, we indeed have a lot of technical issues during setting up this. Like the deduplication is one of the techniques we use. We will not download all the resources by the duplicate links. We first do a deduplication on the links and only download the resource once. And for archive HTML, it has a rate limited. So we use R5. That's another platform provides service for wrapping the archive LaTeX into HTML. We use that page for downloading. And for the Semantic Scholar, and the Hugging Face we download is DOM dataset instead of crawling it. So this can relieve the burden when downloading resources and extracting the tables. And the deduplicating of the tables can relieve our burden for doing the retrieving over it.
Just a small question. So I'm curious why you use precision at 1 as your evaluation metric for
Yeah.
experiments. Is that an arbitrary choice?
Yeah, thanks for reminder. I forgot to say it. So here, we just see that our link count distribution is very high. It's much higher. So our link count distribution is much higher than the previous distribution over classical data lakes. So, for example, each query table has 20 other tables. So their record score can be meaningful. But in our case, the record score might not be so meaningful. Because sometimes we have maybe 1,000 of papers and our record score will goes down to 0.001.
So that's why you focused on precision rather
Yeah,
than
yeah, yeah.
why precision at 1? Is that
Because we try to plot the from K to 1 to 10, and we found there are not some very new information or new findings over it.
see, it's common art. We did precision at 5, you reach the same conclusions.
Yeah, yeah, yeah.
Okay.
Maybe a general question for the for modeling, like do you see a different kind of queries being more interesting in specific for modeling rather than general data lake? For example, for modeling, there are particular model configurations, which is not, like maybe they're not stored in the table of the paper or something, or there's different versions, like you mentioned earlier, different versions of fine-tuned models. Like for that, there are different set of queries that might be interested rather than standard data for the table. Because it seems like you're trying to extract a table information from the model lake and then become a traditional data lake problem where you can apply the existing data lake techniques. But it's then like you or like you use that queries because show to work. For example, what is the best model given the set of models in the data in this model lake, like where those kind of very specific model queries that you might be interested to explore for modeling.
Thanks for your questions. Currently, our focus mainly on this kind of example. Sorry, wait a minute. So currently, we only focus on the minutes of using some performance or configurations table as the query to get some. And currently, we don't include go too deep into this meaning to find more fine-grained meaning on this query table. So we might examine this in the future. Yeah.
Yeah, just think about contributors there. I mean, the traditional, problems, but you might want to then potentially explore like the different dimensions.
Yeah, we believe that this is our first step, try to bridge the data lake and model lake, and we will try more classical or well-defined tasks over data lake to find its new meaning in the model lake in the future work.
Yes.